Good morning. Today we are going to continue our discussion of single stage amplifiers, just making sure that we review them and we understand them deeply. And today our focus would be, last time we talked about the bipolar transistors and in great detail, so now we're going to talk about the MOSFETs. And in the process, one of the important things to observe is what are also the commonalities and what are the differences, and where do they come from, and what are the implications for the design. As you will see, these commonalities and differences will have implications for the design, as will the economical aspect of it, and what's expensive and what is cheap, on-chip versus off-chip. And that's why we will see as we go forward that the topologies that you use for integrated design can be substantially, kind of like when you look at them, completely different from the ways that you implement things as a discrete device. So, having said that, let's start with the MOS amplifier. When we did the parallel treatment of the basic common source and common emitter, and also we talked about the ATD, arbitrary three-terminal device, we looked at the basic MOSFET amplifier. And what we did there very quickly was that, so if you had a common source with no degeneration, meaning no resistance in the source, you had a V in and V out that looks like this, and you had a resistance in RD in the drain and a VDD. And what we saw is that essentially what you have, you can think about this, there's a quadratic behavior, or in more generally some sort of a nonlinear behavior, and in velocity saturated they can be even somewhat linear. But regardless, there's a W and L for the device, and then you have a V in, V out. Let's say if it were quadratic, then this current, from a large signal perspective, what was mu n Cox over 2 times W over L times V in minus VT, VGS minus VT of this guy. So if you write that first order equation, what we'll get is that from a large signal perspective, V out would be VDD, this voltage, minus the voltage drop across the resistor, which is RD times ID. Now ID is mu n Cox over 2, W over L, VGS, which is now V in, minus VT, the threshold voltage, squared. And if we ignore the channel length modulation, then this equation basically is a relationship between V in and V out. You can also throw in the channel length modulation. You can say 1 plus lambda V out, and then that becomes an equation that you need to solve. And you can solve that. It just makes it a little bit more complex, but it doesn't add any additional insight. And we know these are approximate to begin with anyway. So if you look at the V in, V out DC characteristics, V in, V out, what you see is something like this. You start from, if the V in is 0, and assuming that the threshold is positive, this transistor is going to be off, so there's no current, so you're moving this way. Once you hit the VT, you start moving this way, and the transistor, basically, you get the quadratic behavior of the transistor until at some point you get into the triad region, and this is the line V out equals V in minus VT. So here you're in the pinch off, and here you're in the triode region, and we had something like this, which we derived last time. So that should not be very surprising. Now, as you can see, this is quite nonlinear if it's quadratic, and also it depends quite a bit on the parameters, right? So the question is, again, the same treatment. If we want to make this more linear, more controlled by the outside parameters as opposed to internal parameters of the transistor, how do we do that? One of the pathways that you can take is basically by introducing a resistor in the source, which is now we'll be calling it source degeneration, as opposed to emitter degeneration. Or in general, would be terminal 1 degeneration, right? Whatever that is. Now, the other thing that, by the way, I should have said before I got to that one quickly, was the load line perspective. So basically, this is if you have an ID versus VDS plots. We know that they kind of look like that. For a MOSFET, here you are in the triode, and there you are in pinch off. And the load line associated with this particular resistive load is a simple line going from here to there. So this is basically VDD over RD. This is VDD. And as you can see, as you change the these are for different VGSs, which are different VINs. As you change the VIN, the operation point moves, and you go, your output, which is the VDS, is going to go down, this is consistent with that picture on the left-hand side. So now, going back to the case of degeneration, if we introduce a resistor in the source, let's call it RS, and you have an RD, and you're taking your output from the collector, the drain, and your input is applied to the gate. So this is a basic N-type common source with source degeneration. And the question is, what is the gain of this thing? So let's do it a simple one first. Let's ignore the channel length, the body effect. Sorry. So there's particularly in an integrated MOSFET, you have the bulk that you have to think about. So let's say we don't worry about that. Let's say there is no body effect. What was body effect, to refresh your memory? Body effect was the change induced in the threshold voltage because of the change in the width of the depletion region that's formed underneath, which changes essentially the field that appears across the oxide. So that change in the threshold really is the change in the field appearing across the oxide, because by definition of strong inversion, the surface potential has to be 2 phi f anyway. It's induced by the increase in the width of the depletion region, but it appears really across the gate. We talked about this in great detail. If you don't remember, you need to refresh your memory, look back at the discussion we had about it back then. But regardless, so it's a change in the threshold voltage due to the change in the source bulk potential. So let's ignore that for a second and see what we get. So if we ignore that, what does our model look like? Again, using the rule of thumb of whenever your source is not at a fixed potential, it's connected to another thing, T-model will usually works better. So let's use the T-model. The T-model we'll be using is going to be a very simple one right now because we are ignoring the body effect. And let's say we even ignore the channel length modulation, the RO. And we'll bring both of them back very quickly. But let's just look at this first and see what we get, to get the core insight. So what is this resistance in the T-model for the MOSFET? So this is basically source, right? And this is the drain. So what is this resistance? What was it in the bipolar? It was alpha Rm, right? So now what is it going to be? What is the alpha in a MOSFET, in a classical MOSFET? Alpha is 1, right? So this is going to be Rm. So this is, let's call it IS. And what is this current going to be? It used to be alpha IE. So now it's alpha IS, it's going to be just IS. And that makes sense because these two currents being equal, what would that make this current at low frequency? So it makes this DC current 0, which is what you expect to go into your gate anyway. So that dependent source makes that current at low frequencies identically 0. It forces it to be 0 all the time, which is what you expect from a MOSFET, right? I mean, if a classical MOSFET model, you don't expect any DC current to go into that capacitor. Of course, we've talked about some of the non-idealities that arise from the thin gate oxide. There's tunneling current going into it. There are other things. And of course, as we go to AC, then that's not the case. But for now, that's what you have. So if you have this model, and this is RS. So what is the gain of this? So the gain, according to this model, it should be almost easy to determine by inspection, right? We can use either the insight we derived last time, or we can do it directly. Let's do it directly, and then talk about the insight briefly. So the current IS is this voltage. We know this voltage is Vin divided by these two resistors, right? So that's IS. And that IS is being pulled out of RD, which is this resistor, RD. So the voltage drop across this thing is going to be negative IS RD, which is going to be negative V in, so let's call that V out, is going to be negative V in divided by RS plus Rm, which is this resistor, times Rd. And therefore gain, according to this, is going to be negative Rd over Rs plus Rm, which should make sense from an insight perspective because the current in the drain and the current in the source are the same, right? So the voltage drop at the input appears across the source, which is divided by these two, and the voltage in the drain is determined by the current going through the drain. So the rule of thumb is the total resistance in the drain to the total resistance in the source, if you ignore all these other effects, right? So again, you have, in this case, you have the negative of R drain total to the R source total. So again, if you are trying to design very quickly an amplifier with a certain gain, the first point we start with is a ratio. If you want to make this gain 10, you make this ratio roughly 10. Right? And you think about what RM is. So if your RM is 100 ohms, and then you make this ratio with a resistor of, let's say, 1 kilo ohm and 100 ohm, then you can expect your gain not to be 10, your gain would be 5, because you have 100 plus 100. You have the RM, which was 100, and your explicit RS, which is 100. So but if you make it out of 10 kilo ohm and 1 kilo ohm, then you will get a ratio of 10 over 1.1, or 100 over 11. So you'll get 9, roughly, instead of 10. Or you can take that into account and make this whatever it needs to be and get that exact gain, if you're really looking for it. But again, you want to have these in the back of your mind in terms of when you're designing what are the primary first order things. So now, that's really first order. So let's make it a little bit more interesting. Let's add the 9 ideas. So let's now talk about actually what does the body effect do. So let's add the body effect part, the body part. Now, what is body effect? There's another way of thinking about it. Why would it be different? Well, because you essentially have a second transistor. You have that backgate transistor, right? So you have a circuit with two transistors operating not necessarily completely in parallel, but kind of like operating simultaneously. So what does that model for that transistor look like? So you have this RMB, and then you have what we call IS2. So if we call that IS2, let's call this IS1 to differentiate them. And they share, these two transistors share the same drain and same source. They have different gates, but they share the same drain and same source, which basically makes it a 4-terminal device. Right? So the two transistors that share the same drain and share the same source, but they have different gates. So, and where is this gate connected? The back gate. Well, the back gate is connected to a fixed potential because it's basically connected to your substrate, generally. Now, depending on how you implement this transistor, this may or may not be the case. So let's talk about that briefly as a side note. The way these things, the most vanilla, the most standard way of implementing these is that you have a substrate. So this is the cross-section of substrate. Now, the most basic transistor you make, and again, the modern processes may have more levels to this, is that you have an N+. Let's make this a different color, I suppose. So you have an N+ and an N+. And then this is a P-type substrate. And then you have the gate oxide, and then you have the gate. So this is your NMOS, right? So if you're doing this, this is connected to this gigantic substrate. So the substrate, the back gate is connected to some ground. It's sitting on some sort of a fixed potential. So your bulk is fixed. You cannot control the bulk independently. So you say, well, if my gate is fixed, why do I have to worry about this thing? Well, you worry about it because it's the bulk source voltage, like the gate source voltage, that determines the thing. Yes, your bulk is fixed, but your source is moving. So you are inducing a voltage across that controlling terminal of that back transistor, which would induce a change in the collector current, or the drain current in this case, actually, not the collector. So now the difference here is that the PFETs, so that's an N-FET. The PFETs, again, to create isolation, you need to create an N-well. And what you do, you create an N-well, and inside that N-well, you have a P+ and a P+, and then you also have to have an N-well contact. So you have a contact here, N+, that determines the potential. So now you have the ability to connect this to certain things. Of course, you want to make sure that you connect it to whatever you connect it doesn't forward bias this diode. Because this diode, this reverse bias diode is used to isolate this transistor from other transistors. Right? So that's what we call an N-well. It's made in a well. But one option you have is to connect it to your source. So in this very basic vanilla process, you have the option of attaching the source and the bulk to each other. And if you do that, you've essentially shorted across this RMB, right? Because that's the source, that's the bulk. And if you short across this RMB, obviously IS2 is going to be 0, and therefore this current source is going to disappear, so this effect is going to go away. You may say, okay, well, that's great. I can get rid of it, at least for my PFETs. And that's true. You can get rid of it. And there's a cost for it, which is that now your source sees a much larger capacitor, because now all the capacitors of this diode is also hanging off of your source, which will have an impact on the speed. So there's a trade-off there. Again, we'll come back to this. I just wanted to kind of plant this in the back of your head. And then we'll continue, and we'll come back to it. But anyway, going back to this discussion, so let's say we are not getting rid of it. Let's say you are in a scenario, and for an NMOS in a classical process, we can't get rid of it. Actually, there are processes where you get a twin well or twin top process, where you can actually have separate wells for NFET and PFET, and you can control them independently and bias them independently. So if you really need to get rid of the body effect, you can do it for N well and P well. That's an option on the process. Some processes have it, some processes don't. When I say talk about process, I mean the fabrication process. Okay, so let's go to this. And in this case, the way this is, where is this connected in the classical case? Where should I connect this terminal? To the ground, right? Because it's a fixed potential. So the changes in IS2 are induced really by changes in the source voltage itself. That's what induces the changes here. That's what induces the changes in the current. So where are we going with this? Let's see if we can analyze this. So what we are trying to find out is the gain, the new gain for this thing. Right? How do we do that? Well, you can look at this and you can make an observation. You can see that this resistor is really in parallel with this resistor. Right? All I need to do is just take this, rotate it, and bring it down here. Take this, rotate it, bring it down here. So I'm going to detach it from here. They're both ground. So I'm going to leave my ground here, take this, turn it around, flip it upside down, ground. So now this is going to be IS2, and this is going to be RMB. So this is exactly the same circuit. It's just redrawn. So now it becomes more clear what IS1 and IS2 are. One of the things I need to calculate is basically this total IS, right? This IS is basically IS1 plus IS2. So that's the total current that comes out of the resistor, which determines my output voltage. So V out is going to be negative RD times IS, which is IS1 plus IS2. That's the total current that's being pulled out of that resistor, right? So now the other question is, how do we determine IS1 and IS2? Well, there's a relationship between IS1 and IS2, right? That relationship is relatively simple if you look at it. This current is IS1. It's current divided between these two. So IS2, do you agree that IS2 is negative IS1 times this resistive divider, which is basically RS divided by RS plus RMB? This calculation is a little bit, I mean, the algebra here just takes a few lines, so you have to bear with me, but we get to some meaningful results after. It's not that bad, but just we'll have to just carry through it. So this is the IS1. So therefore, IS, which is IS1 plus IS2, is going to be IS1 minus IS1 times this, which basically makes it IS1 times 1 minus this thing, 1 minus RS over RS plus RMB, which you can also simplify to IS1 to RMB over RS plus RMB. So we have this expression for IS in terms of purely IS1. So what is left to calculate, and if you know IS, you know your V out. So the thing that's left to calculate is IS1 in terms of V in, right? Because then we can plug it in and you have an expression for V out in terms of V in, which would give us the gain. So nothing magical is happening, some basic algebra. So then what is happening here? So what is IS1 in terms of Vn? Well, that's not that hard to calculate, right? It's this voltage is dropping across this resistive combination. So we need to just calculate. So we know that IS1 is this voltage divided by this combination of resistors. So it's Vn divided by what? Rm plus Rs parallel RMB. Does everyone agree with that? That's the total resistance between this and ground. So I need to calculate this. So now I have to do a little bit of algebra, right? So I just Vn, need to simplify this. Generally would like to keep this in this form. These are, the late Professor Middlebrook of Caltech. He had an expression for these. He said he used to call them low entropy forms of equations. There's high entropy form and low entropy form for equations. This is a low entropy form for writing Rs times RMB divided by Rs plus RMB. So whenever it has meaning and insight for us, we'll do that. Now, in this case, it happens that we need to kind of expand it because it's going to get multiplied by this thing, and you will see it's going to simplify. So we need to expand it to get that simplification. But in general, we'd like to keep these low entropy forms. So anyway, so we'll do that. We'll go to the high entropy form for a second. So it's that. Or you could, or conversely, you can just bring this to the numerator. You can say Rs plus RMB, and then multiply this out, which will create Rs Rm plus Rs RMB plus Rm RMB. The sum of the two-way products of these things. And then I plug this back into this guy, and you can see these guys are going to cancel. So what we get, or why don't we plug it just straight into that guy? V out is negative RD IS1, and IS1 I plug in from this one, so I get an RMB over Rs plus RMB times this thing, which is Rs plus RMB divided by Rs Rm, the high entropy form, Rs RMB plus Rm RMB. These guys cancel times V in. So gain, according to this, is going to be negative RD. And now we have this guy, these guys. So I'll divide this denominator by RMB. So I can get rid of that guy. So what are we going to be left with is RD divided by, so you get, here you get an Rm. And what do you get here? You get Rs, right, plus times 1 plus Rm over RMB. But Rm over RMB is something, it has a name. It's the ratio, or the inverse of the ratio of the strength of the transistors. Remember, there was this parameter chi, which we defined as Gm over GMB. The ratio of the strength of the transconductances of the two transistors. And we said it's like 0.2, 0.1, 0.3, depending on the transistor. So the back transistor is about 1/5 to 1/10 weaker, or 10 times weaker, or 5 to 10 times weaker, which basically becomes RMB over Rm. This is actually, sorry, this would become the, yes. No, sorry, the other way around. This is GMB over GM, and this is Rm over RMB. Sorry. It's the ratio of the back gate to the front gate, which basically, since it's weaker, it's less than 1. So GMB to GM is 0.1 or 0.2, and therefore Rm to RMB, so RMB will be larger. That's also chi, which basically makes this expression 1 plus chi. So what has changed due to the body effect? Let's look at. So this is the expression for the gain with the body effect. That is the complete expression. Now, what do we learn from this? Well, let's compare this with that. I can rewrite this so that it looks even more similar to that. I can reorder them, Rm plus Rs. So what do we see? Or Rm plus Rs. When you compare this to that? So what is this new rule? It says it's the ratio of the total resistance in the drain to the intrinsic resistance of the source plus the extrinsic scaled by 1 plus chi. Well, remember, the reason you have this thing is that you're really trying to lump the effect of two different transistors into one expression. And it's a relatively simple expression to capture the effect of two transistors operating simultaneously. So what it says is that really the explicit resistor that you put there gets scaled by 1 plus chi. Now if chi is 0.1, it's a 10% error. If chi is 0.2, it's 20% error. And you see this scaling happening a couple of times in a few of this expression that we're going to derive. So yeah, it's scaled, but still, it's the ratio of the total resistance in the drain to the total resistance in the source with one adjustment for the total explicit resistor. So still that expression is quite useful. This is just like a correction to it from a design perspective, right? So yeah, fine. But it allows you to calculate it. But other than that, it's fine. And it takes that effect into account. Now, of course, if your back gate is somehow connected so that you don't have the body effect, that chi disappears. Again, this is, in my opinion, this is a superior form of writing the gain, because it shows it as a ratio of resistors. It may look less fancy, because you don't have the GM, the drive capability versus the, the load, etc., and we will switch back and forth. Sometimes we write it in the other form. The form that textbooks generally write this is this. They multiply everything by GM, the numerator and denominator. So that would be the more familiar form. If you have seen this before, it would look like GMRD divided by 1 plus GMRS 1 plus chi. Now, which is the same thing. And the way the interpretation of that form is, this is the intrinsic gain. This is what you had originally, which we didn't write here really. The AV of this thing was negative GM RD, or negative RD over RM. And the gain is reduced because of the source degeneration by this factor. This is the reduction in the gain. Yeah, I mean, that's an alternative interpretation. But I think this interpretation is more conducive to design, because it helps you pick values more clearly and directly if you're making a design. You're just analyzing something. I guess it doesn't matter. Any of them would give you the same number. All right. Any questions on that so far? All right. So that's one of these aspects. The other thing that we need to take into account and think about is, what is the output resistance and input resistance of this stage, right? We've talked about these things. So let's briefly talk about it. What is the input resistance? Well, how do we calculate the input resistance in general? I mean, it's trivial in this case, but let's just think about the general procedure. You can apply a test voltage or a test current and measure the other one. If you apply test voltage, you measure the current. If I apply test voltage here, what is the current? 0. So the ratio of the voltage to current is going to be infinity. So the low frequency input resistance of this classical model for MOSFET is infinity. It's another way of saying beta is infinity, right? Because alpha is 1. And beta is alpha divided by 1 minus alpha. So it's 1 divided by 0. Anyway, how about this output resistance? Now, the output resistance requires a little bit more work. And it's necessary, and it's important to understand it, because you will see when we try to make more sophisticated stages, it will have an impact. So this is a necessary calculation, and we've done a good chunk of it already, so it's not going to be that hard. So for the output resistance, what is the process we use? We say you have the IS1, you use this thing, and so you have the small signal model, but what's happening to the gate when you try to calculate the output resistance? The way you calculate the output resistance is you null all the independent sources. You set them to 0. So your input voltage source is nulled, which basically means that this is shorted, right? And then now we have to, of course, put the RO there. And then you have the other source for the bulk. So you have, so this is RM, this is RMB, this is IS2, IS2. And then this is basically, we are looking at the intrinsic output resistance. Of course, that will be in parallel with RD. So we are looking at what we see here. So we call it R out prime. And then whatever that is, the total R out is going to be basically R out prime in parallel with RD. And then here you also have the RS. So you're trying to calculate the resistance looking into here. In other words, you're applying a Vx. So you're applying a Vx, and you're measuring Ix. So the question is, what is the relationship between Vx and Ix? And we have to do the calculation. But if we look at this circuit a little bit carefully, you will see something you can observe. You can make a few observations that can simplify it. You can see that these three resistors really are in parallel, right? Because the other terminal of them is, one terminal is common, and this terminal is also common. They are all ground. So I can basically take these, we can take these and bring them down here. So I can take this, detach, flip it down here. So I can put this guy here, RMB, IS2, and I can put this one here, RM, IS1. Get rid of this, get rid of that, ground, and ground. Okay? We can simplify it even more. We can say, look, the combined current IS1 and IS2 of these two determines the combined current here. So I can just lump all of them into IS. So you can say, I can get rid of one of these sources and say, look, this is just IS, which is IS1. So this is IS, which is IS1 plus IS2. And that's the current going through the parallel combination of these two resistors anyway. Okay, so I can get rid of that 2 and say, look, let's call this IS, and let's call this RM parallel RMB. We agree that this is still the same thing. So now it's starting to become easier, right? Think before you act, always. Just that. Now, okay, so what is this current? Again, we had a similar argument with the BJT. This is an RM at most. It's on RM parallel RMB. So this parallel combination of these, all of these things is going to be less than RM. This is an RO. So if the ratio of RO to RM is not large, then we are wasting our time anyway, because that's the intrinsic gain of the transistor. So if that ratio is large, we can say, well, this is really dominated by RO, so this current is approximately Vx over RO. It's a large resistor in series with a smaller resistor. So roughly that's what it is. And that basically sets, if that current is known, then this IS1 as a function of that is going to be negative. So that's that. So IS1 is going to be negative of Vx over RO, which is the total current divided between these guys, which is going to be Rs divided by Rs plus RM parallel RMB. Okay, basic calculations. And that is what's going to come off of here. So what you're going to get, the total current Ix is going to be Is plus Vx over RO. But Ix is given by this. So basically you can factor Vx over RO. It would become 1 minus Rs over Rs plus Rm parallel RMB, which is Vx over Ro, Rm parallel RMB divided by Rs plus Rm parallel in parallel with RMB. So that's Ix in terms of Vx, right? We agree? So essentially we have our R out prime, which is the ratio of Vx over Rx. So R out prime you write R out prime is going to be, which is defined as Vx over Rix. From this is going to be Ro times this thing that we need to now simplify, Rs times Rm parallel Rmb divided by Rm parallel Rmb. Do we agree? Did I make a mistake somewhere? No? All right. And that requires some simplification, so that's Ro times, this is 1 plus this ratio, Rs divided by Rm over Rmb. And now we can simplify it a little bit. So how can we simplify it? We can write let's write Rm parallel Rmb. Rmb is Rm Rmb divided by Rm plus Rmb. But we know that Rm over Rmb is chi, right? We wrote that, we have it in purple up there. So divided by Rmb, you get Rm yes, Rm divided by, so this becomes 1 plus chi. Right? So we plug this into here, in this guy, you can get Ro 1 plus Rs times 1 plus chi divided by Rmb. Oh, I'm sorry, Rm, not Rm. Rm. Which you can also write as Ro times 1 plus Gm Rs 1 plus chi. Again, you see that the effect of that extrinsic resistance in the source, because of that backgate effect, is multiplied by scaled by 1 plus chi. So if your chi is 0.1 or 0.2, it will increase it by 0.1 or 0.2. So it's not necessarily a bad thing. This is not necessarily a bad thing, because your output resistance is now becoming a little bit larger. Again, you have to differentiate between, this is really a second order effect. It's like a 10% thing, right? If something is low tens of percent, that's second order. If it's in hundreds of percent, like a few hundreds, it's first order. And if it's in few percents, it's second order, third order, really. Right? So, at least for us in this context. Okay, so your output resistance is, again, scaled by 1 plus Rs over Rm, but factor of, so basically it's scaled by the same factor that your gain is reduced. You can see it from either one of those equations, this form or that form, right? I mean, if you look at this form up here, you will see that due to the degeneration in the source, your gain is reduced by the same factor that your output resistance is increased. Okay, fine. So that's what it is. So now that we understand the basic properties of this real, kind of like this stage, this common source stage, let's see from a practical implementation some of the variations and discuss some of the variations. And some of these have some interesting properties that we discussed for the sake of their interesting properties. And some of them are things that we are interested in because they have implications in the design. So one of the things that we said, so let's just start maybe keeping these here and move to the next whiteboard. So let's say we want to make a simple, let's go back for a second to our stage with no degeneration, and we are trying to get gain. But let's say we have another constraint for the sake of argument for right now. This constraint may or may not exist in your design, depending on the parameters. But let's say the other constraint is that, like we said, the passive devices are big and expensive. And active devices, transistors, are cheap and small. So they are expensive because they are large. So let's say you want to make the load, but you don't want to make a load in such a way that a resistor is an expensive load, let's say, if you wanted to make that. And there are scenarios where this is the case. I mean, the resistor can be large, so you want to make something small, and you don't want to use a resistor. So what kind of loads can we use? What can we use instead of, so we initially had this RD, right, to VDD. So this was the V in, and this was the V out, and this guy had the W over L. It's called W1 over L1. And it's, let's say it's the load, but we don't want to use a resistive load. Let's say we want to get all of our loads, see if we can get, what can we get out of transistors themselves. Because that would make it smaller, etc. And we'll see it has some other interesting properties, and we'll see variations of this load and different kinds of load that we can use. So we want to use another MOSFET as a load. Okay, let's start with something, and we'll talk about, and we'll see what it does, and then we'll look at variations of that. Let's say I use another NFET, NMOS, but I use it in a funny way. I short circuit the drain and the gate of this transistor. So it becomes a two-terminal device, right? Essentially make it into a two-terminal device to replace my resistor. Now, what are the properties of this load? Is this a good load, bad load? So I'm connecting it again off of the VDD. So this is hanging off of the VDD here, the rail. And you have, so this becomes your V out. The question is that, what are the properties of this load? This is, by the way, sometimes called the quote-unquote diode-connected MOSFET. Because if you do this to a bipolar transistor, you will get a p-n junction diode, right? Because you will get the base emitter diode. That's how you make a diode out of a transistor, right? When you just basically short circuit the collector and the base, you're left with the base emitter diode. So this is also called a diode-connected MOSFET, although technically it's not a diode. Well, it's a diode, it's not a p-n junction diode. I should take it back. It is a one-directional load. Okay, but let's see what it does. So how do we know, what can we say about this? How can we characterize this? Well, we can look at the large signal one, so let's call this ID. We can write a relationship between V out and ID. Now, first thing we need to know is that what region of operation the transistor is in, because they have different equations, right? Different regions of operation. So what region of operation is this transistor in if your VT is positive? If your threshold voltage is positive? What is what are the conditions for, what are the requirements for different regions of operation? What is the constraints to be? Let's say for the transistor to be on, to start with, what is the what do we need to happen? What is the, yes?
VGS is greater than VT plus.
Just VT. VGS needs to be greater than VT. I mean, for us, by our definition, for the transistor to be on. Of course, we know that below that there's sub-threshold current, et cetera, but for the basic classical model is VT has to be greater than, VGS needs to be greater than VT. So basically, this voltage needs to be at least a VT below VDD for this transistor to be on to begin with. So if I look at some sort of an IV characteristic, so this is ID versus V out, this transistor, according to our simple model, is off up until VDD minus VT. So if this voltage is higher than VDD minus VT, the VGS is not even above the VT. So other than subthreshold, which we are ignoring for this time being for a second, it's nothing. There's no current. Now, when it turns on, what region of operation is it going to be on? In. So basically, let's say this V out is smaller than that. What region of operation are we going to be in? Again, we have to look at the constraints for different regions. There are two regions, right, when it's on. There's pinch off and there's triode. The requirement for pinch off is that VGS minus VT is smaller than VDS, or VDS is greater than VGS minus VT. So what is VDS? Do you agree that when you connect it this way, VDS and VGS are the same? So then VDS, if VT is positive, VDS is always greater than VGS minus VT. Right? Because it's the same number divided, another number subtracted from it. So it is going to either be in off or pinch off. So it's going to go into pinch off and remains in the pinch off all along. So if it's in pinch off, we know its current voltage characteristic. So then what we know is that we know VDD minus VT minus V out, or let's say minus V out minus VT, because this is VGS, this is the VGS. VDD minus V out is the VGS here. VGS 2 minus VT, VGS minus VT squared times mu n Cox over 2 W2 over L2. That's the current. That's ID. We're ignoring the channel length modulation for the time being. That's basically just the basic quadratic equation that you get. Now, if I plot this, what do I get? You will see that you get a quadratic curve like that. And here you get whatever you get if you set V out to 0. OK, so that's the load line. That's a new load line. And remember, now, so this is different from a resistive load line, because the resistive load line looked like this. Right? This was the resistive load line. So this is a new load line we've defined with this load. So we are making it, essentially what we are doing, we are making a stage that looks like this. W2 over L2, and that's what we are looking at. Okay, so with this, what is the input-output characteristic? What are the? Is it a good? First of all, is it a good load line, bad load line? Do you like this load line? If you don't like it, tell me why. So remember, this load line intersects with these for different Vins. Vin 1, Vin 2, Vin 3, etc., etc. So as we are changing the Vin, this operation, with the resistive load line, you went from this point to this point to this point. With this load line, you're going from this point to this point to that point. Is it better or worse than the resistive load line, in your opinion? And if it's better, why? If it's worse, why? Or what are the advantages and disadvantages of this load line compared to a resistive load line? So let's talk about that. So what are your thoughts? Do you like it better or worse than the resistive load line? Worse. Why? Did you say better or worse? Worse? Why worse? Less horizontal, right? So it provides less gain, it appears, right? Does it have any advantage? Well, let's find out. Let's see. Let's write the expression. So we know this is ID, right? So this is the ID of this thing, which is the same thing as ID here. So let's write the large signal equation. And that ID is mu n Cox over 2 W1 over L1 Vin minus Vt squared. And this is really Vt1 and this is really Vt2 because of the body effect, the threshold voltages may differ. But we can take it into account or not, doesn't matter. So what do we learn from this? So this is basically the ID, right? So we can look at these two expressions. Of course, you can cancel these two. They're both n-type, so you can cancel that. And then what you get also is you can divide both sides by double. You can solve for V out versus as a function of Vn. And when you do that, you get V out is VDD minus VT2 minus. So when you before you do that, you need to take a square root of both sides because both sides are squares. You get square root of W1 over L1, W2 over L2, Vin minus Vt1. So that becomes a V in, V out relationship. And as you can see, if I ask you what's the gain, if we ignore the body effect, so let's assume that Vt is constant for now. It's not a function of V in or V out. What is the gain? What is the small signal gain? You should be able to tell me from this expression, right? Yeah.
It's just negative with the stuff that's in the square root.
Yeah, negative of the square root. The ratio of the ratio of the W over L's. It's the square root of the ratio of the W over L's, right?
Could you repeat the assumption?
The assumption is that there is no dependence on Vt1 and Vt2 on V out. But we know that Vt2, if this is connected to ground, will be a function of the V out because of the body effect. So this also has some dependencies. So it will have some, it's not a constant. But I'm just assuming for now that that's constant. The two VTs are constant. They're not going to change with the output voltage. If you make that assumption, and we'll correct that assumption in a few minutes, or modify it and see what impact it has. But for now, let's assume that. So with that assumption, you see the gain is basically the derivative. It's dv out to dv in, which is basically this thing. Okay? Is that a good thing or a bad thing? Do you see anything positive in the gain being defined this way? Because our gains before were some sort of a ratio of resist RD over RM, right? Or GMRD, right? For this stage. For this stage, it was GMRD, right? Negative GMRD. So now it has become square root of W1 over L1 divided by W2 over L2. It has less distortion. Okay, so yes, correct. Can you elaborate a little bit more? Why does this have less distortion? It's linear, right? First of all, it's a large signal behavior that has become linear. It's not the small signal one. Of course, the small signal one is always linear by definition. But this is a large signal characteristic that has become linear. And furthermore, it also does depend only on ratios of lengths or the physical dimensions. So your gain is defined by ratios of physical dimensions. And this is usually a good thing because it makes it less dependent on environmental parameters, things of that sort. If the temperature changes, things of that sort, that would not affect the gain as much. So in general, we would like our gain to be defined as ratios of similar things. And this is a general design principle that you will see over and over. That ideally you want your gains to be, if you want to make something that's robust, that with temperature change and changes in the parameter of the supply or the process changes less, you want to make sure that your parameters of design, including gain, the parameters of interest, are defined as ratios of similar things, ratio of resistors of similar kinds, ratios of lengths. This is actually ratios of ratios. So that could be a positive thing about this thing. Yes, you'd get less gain, that is true, but that's a positive thing. So let's see. If I wanted to make this gain large, what do I need to do from a design perspective? Because my design parameters are W1 and L1. When you make a MOSFET, you can choose its W and you can choose its L. Of course, there's a minimum length that you cannot go below, but you can make the W and L within reason, whatever you want. So how would you choose them if you want to increase your gain? Yes?
Make W2 really small, L2 really large.
Right.
L1 really large.
Make L, exactly, make W2, this one small, this one large, this one large, this one small, right? And yeah, I mean, you can do it to some extent. So let's say you make this ratio, what can you make it? So let's say you make it 100 to 1, and you make a very long transistor, very narrow one, let's say another, I don't know, 1 to 10. I mean, you can make it more, let's say. So you get a factor of 1,000, so you get a square root of 1,000, you get 30-ish gain. Right? Yeah, you can do it. I mean, if you're looking for really high gain, this is probably not your cup of tea. But if you're looking for something that's stable and doesn't change that much, this may be something to consider. Okay, and we can see it also from small signal perspective. So let's do the small signal perspective really quickly. So from a small signal perspective, when the transistor is connected this way, let's look at the model and see what it looks like. So for that top transistor, so you have this grounded, and then you have the RO, if you want to really think about. This terminal is grounded. This terminal is grounded. No, sorry. This terminal is not grounded. This terminal is connected, shorted here. That terminal is grounded. And then you have the RM. And then you have the RMB. And then you have this guy connected. And you want to see what is the resistance seen looking into here. What is the equivalent resistance? Because that's your load resistance, right? From a small signal perspective. It's that effective load resistance. So do I have to worry about this current source? No. Because this terminal is actually shorted, so it's shorted across, so whatever current it has will flow inside this loop and would not affect anything outside, right? So I don't need to really worry about that. Do I need to worry about this current source? No, because it's shorted across both sides. So again, whatever current it induces. So what do I have looking into here? I have this resistor connected to ground here, this resistor connected to ground, and this resistor connected to ground. So what is my total resistance? Seen? It's the parallel combination of those three resistors, right? So what we see here is Rm parallel Rmb parallel RO2. So Rm1, Rmb, Rm2, Rmb2, and RO2. It's a parallel combination of those three resistors. That's what the load is. And what do you see looking down? So if again, going forward, we'll look at this as write Rm2 parallel Rmb2, and going forward, we will not write RO2, but let's for now write it, because that's much larger than those two. And looking down, what do you see? What is that resistance you will see looking into the drain of this transistor? Or RO1, right? Because the source is grounded here, right? So you see basically RO1. So what is the total load resistance? It's Rm2 parallel Rmb2 parallel RO1 parallel RO2, which is for all intents and purposes Rm2 plus parallel Rmb2. And what is the drive? There's a current source driving this. It's the GM. So it's GM1 Vin, if this is Vn. So that is the AC drive current. Now that AC drive current is being pulled out of that node that has this total resistance to ground, which is Rm2 plus parallel Rmb2. So what is the total gain? It's negative GM1 from a small signal perspective is negative GM1 Rm2 parallel Rmb2. Now this combination, so you can write what is Rm2 parallel Rmb2. I think we had that here. So in the previous whiteboard. And what we had here was basically, it was Rm over 1 plus chi. So this ratio is basically negative GM1 Rm2 over 1 plus chi. Okay? Which is negative GM1, or you can write it as GM1 over GM2 divided by 1 plus chi. And if you want to see if you get the same result or not, let's express GM1 and GM2 for the specific transistor which we have, which is the MOSFET. You remember we had expressions for this. We had basically 2 mu n Cox W1 over L1 ID divided by square root of 2 mu n Cox W2 over L2 ID times 1 over 1 plus chi. And if you just look at it the way it is, obviously these guys cancel. And then well, if the currents are the same, these guys cancel. And you get this ratio, but there's a correction factor of 1 over 1 plus chi. Because we had ignored body effect here, which now, if you take it into account, it scales the gain down by a factor of 1 over 1 plus chi. So it reduces it by 10, 20% from that. But you can see the same result there from the small signal or large signal. But large signal also tells you that this is going to be relatively linear. And why is it linear? You can see kind of what you see really, I mean, it's easiest to see it in the equations, but you can, when you look at, there's this nonlinearity that's compensated by this nonlinearity, because they're the same nonlinearity. And in fact, you can show that for an arbitrary device where this relationship is some sort of a nonlinear relationship, since this relationship would be the same nonlinear relationship, if you make it for any arbitrary three-terminal device, this kind of load, you can linearize it. Because then you will have the inverse function of this and inverse function of that coming into play. The challenge would be that the gain would be the inverse function of the ratio of the strength or the sizes of these transistors. And if this function is a very strong one, let's say, for example, an exponential, this inverse function is going to almost kill your gain. The weaker the functionality of the drain current with respect to the input is, the more effective this technique would be for an arbitrary three-terminal device, right? So we can basically say if you make this out of a arbitrary three-terminal device, it will look like this, right? V whatever, supply. And this is V out. So these techniques are quite general if you think about them. So you can always, if you need to linearize a device, you can always, this is one of the things that you can do. Have it fight itself. Okay, so that's for that. Fine. And we got the gain and we got the correction factor for the gain due to the, let's say, body effect. But let's talk about this a little bit more. Let me ask you this question. Let's look at this equation again. This was our gain. And see if there are some modifications and changes we can make to increase this gain. So now let's say we are not worried too much about linearity. We are going back on our quest for large gain. Let's see what we can learn from this equation, because equations, like I said, are useless if you don't understand what they mean and if you don't understand the implications and insight that's coming out of them. This or any other class or any other subject should not be an exercise in writing equations. You just write the minimum amount of equations that you need to get to the maximum amount of results. So anyway, here, let's go back to this equation and see what else could we do to these two devices to make sure that we get more gain. If I wanted to increase my gain, well, you can say, I can get rid of your body effect, fine. That would give me 10% more. What else can we do? Look at the equations and the parameters and see what we can do. So can you make suggestions based on those parameters? There are a couple of parameters that canceled out, right? Yes? So if you make it, okay, so that's an interesting suggestion. It says, if you make the top transistor a PMOS somehow, I mean, we have to think about how we bias it, etc. If you made it out of a PMOS, would it help or hurt? Which one would it change? It would change this. Why would PMOS help? You're right, but why would it help? It has a smaller mobility. It has a smaller mu, right? So that's one way to do it. It will have some implications in the design, but yeah, sure.
In PMOS, can you also connect the source to the bulb?
Yeah, so in PMOS you can also get rid of connect the source to the bulk, and you can get rid of that. So if you, but it will, well, the PMOS would be upside down. It would be basically connected like this. But yeah, you're right. And then you also connect the source to the bulk. So the body effect goes away, so you get that 10%. And you, as you pointed out, you can also get the advantage of ratio of that n FET to p FET. So you get a square root of 3 improvement, square root of 2, square root of 3. You get another factor. So you get a factor of 1.5. Okay, so these are good suggestions. But I want you to think about other suggestions you can make. And that goes back to design, electronic design. I mean, you can change the topology. You can add stuff. You can move things around. Yes?
You can change the physical dimensions to alter COX and the ratio of the COX.
The COXes. So that's a true. I mean, you could try to change the COX. But again, that's not an electronic design perspective. That's really a device physics thing. And it's probably, out of all these parameters, the toughest one to change, in the sense that it is possible, but it means that you have to make a thick transistor. But now, what you're saying is not completely meritless. In modern processes, you sometimes have choices of two kinds of transistor. You have a thin gate oxide transistor, and you have a thick gate oxide transistor. So you can actually use your thick gate oxide on the top, and as a result, your COX will be, you have a smaller COX here. And this is a very common option in many of the processes. Because if you want to deal with large voltages, the drivers for the outside circuitry, they have the thick gate oxide that can handle a couple of volts. And then you have the puny but very fast transistors that are really internally operating at lower voltages, and they can operate fast. So that's a reasonable suggestion. So we covered all of these things. We talked about W over L, which was the obvious one. Yes?
You have cancellation of currents. So if
You have a cancellation of currents. So we have to change the current. Well, so let's say you have a total fixed current. How can we change the current? We want to change the current in the sense that the current through NMOS and PMOS should not be the same. So how would you do that? Which current do you want to be smaller? Or not NMOS, I mean the top transistor or the bottom transistor. Let's say the NMOS. The top transistor current versus the bottom transistor current. Which one do you want to be smaller to get more gain?
The top one.
The top one, yes. You can add a parallel current source, right? You can steal some of this current away. You can reroute it. So not all the current that's going through here ends up here. So if you had an ideal current source, you could put that ideal current source here. And if you make this, let's say 0.9% of ID, if this is ID, right? How much your gain would be? Because now this current is not ID. This is ID over 10, right? You have to think about it as design, right? Now, if it's ID over 10, that increases your gain by a factor of square root of 10, which basically is another factor of 3. But if it's such a great thing, how about make it 0.99 of ID? And then this becomes 100, right? So I get a factor of 10. And if it is such a great thing, why stop there? 0.999, and make this a factor of 1,000. And we can keep going forever, but we are not. Okay? So, and in the limit is basically making that completely ID, which appears to suggest that I will get infinite gain. There's something wrong in there, right? What is wrong? Two things are wrong, but go ahead. Yeah.
The current is too low.
No, yeah, but our equation is suggesting something that doesn't appear to be physical, right? What is the assumption? So I've started violating some of the simplifying assumptions that I've made when we did this, right? What are those simplifying assumptions that we violated? We ignored some things, for example, here and here in green. ROs, right? Because ROs are not part of this expression, because we've ignored them. We assume that they're much larger than R. So now ROs start kicking in and say, well, look, you're getting rid of that, but the RO is sufficiently small compared to these other things that RO matters. So your output resistance is not infinity. And you don't have an ideal current source anyway, because that will also have some sort of an RO. But that leads us to the next kind of variation of the gain stages, which is, well, you want a current source up there. And how do we get current sources up there? And the idea, again, is similar to what we discussed in about bipolar transistors, is that you can use a PFET and keep it at some V bias. And you have a VDD. And you have a V in, and you have a V out. So this is W over L, Wn over Ln, and Wp over Lp. And what you have is now, what is the gain of this stage? Well, to understand the gain, first you have to see which region of operation you're in. And this may sound like a mantra that I keep repeating. This is very important, especially when you start designing. When you start designing, even in this class, when you start working with simulators and all those things, the first thing you need to verify is that if your transistor is really in the region you wanted it to operate. If are your transistors in pinch-off region, or are they in some other region? Because if they're in some other region, all this small signal doesn't apply, really, the one that you're using. So you're wasting your time drawing small signals for things that are in pinch-off, that are not in pinch-off. So first things first. So what would happen as I increase? What is the V in, V out characteristic of this stage? So this is V in, V out DC characteristic. How does that look like? Well, you start from Vin of 0. This transistor is off because its input, VGS is smaller than VT. So you need to get to a VT. You need to get to a VT, VTN really, and then you go there, and then this starts turning on. As soon as it turns on, what region of operation is this going to be? This transistor, NFET is in. Its VDS is relatively large, and VGS is small, so that's in pinch-off. How about the PFET? So we know that N is in pinch-off. How about the PFET? Well, what's the voltage here? What's the voltage drop across the drain source of the PFET? Very small though, right? So it's very small, which basically means that its VGS is reasonably large. Probably you biased it properly so that it's turned on. So it's going to be in triode. So it starts off with PFET in triode and NFET in pinch-off. Then, if your voltages are right, there will be a region where both of them are in pinch-off. And this is where your small signal model really holds. And those calculations of RON and ROP hold. It's in that region. And then what happens? Once this voltage starts going too low, and this voltage is going high, then this starts leaving the pinch-off and goes into triode. So N goes into triode, and P is in pinch-off. And that's where you stay, continuing going forward. So it's really this region that we are talking about when we talk about the gain of these stages. And you need to make sure that you design it in such a way that it is. Now, if you use it with feedback properly, the feedback would guarantee that it remains in this region. And that's the beauty of the system. But we are right now assuming that there's some mechanism that keeps it in that region, which we haven't discussed yet in great details. So, but in that region, what do we see? Again, let's go through doing small signals in our head or on the schematic, on the large signal model. So if this is Vn, this current is going to be GM Vn, GMN Vn. And what is the total resistance here if they're both in pinch-off? This is ROP and this is RON. And therefore, the total gain of the stage is going to be negative GMN RON parallel ROP. And we went over similar expressions because GM for MOSFET, for a long-time MOSFET, or non-velocity saturated classical MOSFET, you have 2 mu n Cox, W over L, ID, and then this, both RON and ROP are some L divided by, so let's just write it in more generalities, L divided by ID, some DXD dVds. And you can plug in some numbers and get some values, but one of the things that you see that there's a proportionality with W and L and inversely with ID, which we saw before. And we know that this fails for small IDs, so it's not going to go to infinity for zero current because you're now going to enter subthreshold. And when you enter subthreshold, this is going to behave more like a bipolar transistor. It's going to be exponential. So its GM is not going to be this expression. Its GM is going to be ID over VT, which is going to cancel this ID. So you're going to get to some fixed gain. So the gain versus current is not going to explode, as this equation suggests. Rather, it's going to become a flat value once you get to subthreshold, a fixed value. We've talked about this brief before, but just refreshing your mind. So yeah, so that's what that is. And in terms of load lines, if you think about this, the way it looks is pretty much a straightforward thing. So if you look at the IV character, so this is the load line, ID versus VDS or V out, let's say. So the load lines for the NFET look like this. They are the classical MOSFET expressions for different VNs, VN1, VN2, etc., etc. There's a region here, you're in triode, N is in triode, and N is in pinch-off here. And then the load line for the load, for the PFET, is the mirror image. And it kind of looks like that, where again, here you are in triode, P triode, and then P pinch off. So this green region here is the region where both of them are in pinch off. So these are showing the same thing on different axes. All right? Any questions on this? No? All right, so let's take a break.